In this problem, we predict the motion of the spring mass system given that our external force is this sawtooth function. To proceed, we simply take the Laplace transform of our differential equation. Starting with the y double prime, we get our usual transform of the second derivative. Then we get the transform of the y term. And we had the transform of our sawtooth function, which was a leading term based on the start of this function. And then we had a pattern of -4 over s times all the step function exponentials, simply added together. To predict the motion, we need to solve for y of s. So we'll start at equilibrium. What that means is that our initial displacement is 0, our initial velocity is 0, and so we end up with s squared plus pi squared over 4 times y of s. That equals the same expression we see here on the right-hand side, unchanged, with all our exponentials added together. And so y of s is going to equal a series of terms 1 over s squared times that quadratic term minus 2 times 1 over, there's only one s here, so s squared plus pi squared over 4. Then we'll bring the -4 out as a multiplier. We have an s here, and we're dividing by this term over here, so we have s times s squared, that quadratic again, all times our e to the -4s plus e to the -8s plus e to the -12s, and so on. Before we can do our inverse transform, we've solved for y, but we need to go backwards. We're going to need to break up these terms here into their constituents. Partial fractions will help us do that. Unfortunately, we only have two distinct terms. We have a 1 over s times that quadratic and a 1 over the s squared. We won't go through the detailed steps here, but we end up with something similar to what we've seen before, where we get a over s and b s plus c over the s squared plus pi squared over 4, so this. And it's a nice simple reciprocal here. And it turns out that having an s squared here doesn't make a whole lot of difference. We just get 4 over pi squared times the 1 over s squared term minus 4 over pi squared times the 1 over s squared plus pi over 4 squared. We're now ready to take the inverse Laplace transform, though I just realized we left off this f0, so there's going to be an f0 multiplier of the entire right-hand side, an f0 multiplier of the entire right-hand side, likewise for this term here, and we'll include it more correctly on the next page. Keep an eye open for these common factors. We're also going to pull them out front as well. Rewriting our y of s as many individual terms as we can, simply to make the inverse transform easier. We have the leading terms, we have the second term that came up, and we have a constant term with the exponentials, and we have the decomposition that involved the s squared quadratic and, again, the exponential terms. All of those times the common factors of f0 and the 4 over pi squared. If you consider each of these terms individually, we can find the inverse for each of them. The one missing ingredient is that this is a transform that looks like sine, except it needs a pi over 2 on the top, and to make that work, we're also going to have to multiply by 2 over pi. And the same thing for this term, and the same thing for this term here. That combination here will now give us a sine transform, and likewise here and here. So now we can do our Laplace inverse, and we actually get y of t. So it'll be f0, 4 over pi squared, times, what have we got? That's the transform of t. This is the transform of sine pi over 2t. And it's going to have a multiplier of 2 over pi. Then we're going to have a minus 2. then a plus 2 sine pi over 2t's times 2 over pi. That completes those 4 terms there, all written out here. Next we'll do this sequence. We have a -4 multiplier, and each of these is an exponential for a step function over s means just the step function by itself. u4 plus u8 plus u12 plus and so on. And last but not least, we have plus 4 times a 2 over pi. Now this one's a little more interesting. We have u4, this is a sine function, pi over 2, but it's going to be t plus 4. The step function here, this exponential, gives us the step and a shift. And careful, it's t minus 4 when we're doing the inverse transform. And then we'll have u8, same structure, pi over 2, t minus 8, plus u12, sine of pi over 2 times t minus 12, plus and so on. What makes this workable is that if we look at the shifted version, this sine of pi over 2t has a period of 4, so if we shift it by 4, this whole thing is just sine of pi over 2t. We get back to where we started when we shift by 4. And we also get back to 0 when we shift by 8. And we also get back to the start when we shift by 12. So these sine terms that we get here are all going to be equivalent or equal to sine of pi over 2t. And that's what's going to give us our resonance effect. We'll see this on the next page. Our y of t then will equal f naught 4 over pi squared for everything times our t minus 2 over pi sine over pi 2t minus our constant 2 and plus a 2 times 2 over pi sine of pi over t, pi over 2t. In fact, we could cancel some of those. We'll leave that as is though. What's more interesting and more important is how the rest of the system plays out. We also have a -4 times u4 plus u8 plus u12 plus u16, the step functions. Let's see what else we get with that. Our last terms are going to be 4 over 2 pi times everything turned into a sine of pi over 2t times u4 plus u8 plus u12 plus u16 and so on. Now if you can see how step functions work and think of them as on at 4, on at 8, then on at 12, then on at 16, all times this, we're going to get larger and larger multiples of this sine function. It's easier to see in piecewise though. What we're going to do is simply call this g of t because it's a big mess and it'll be easier to include it later. So our y of t is, on the first part, it's our g of t, and we'll put the f naught, 4 over pi squared, in front of everything here. That g of t has no step function, so it applies from 0 onwards. And then the first change is when we hit our step function at 4. So this will be up to time 4. That function stays on, and then we're going to subtract 4, and we're going to add, let's call it 8 over pi now for this expression, sine of pi over 2t. That's going to be valid when t is between 4 and 8, because that's when the step function 4 is on and none of the other step functions have been activated yet. Then, when we go to 8 to 12, what we did is we added the 8 term here. Well, that just means we got 1 plus 1, that's 2, so we'll have minus 8 with that -4. And we have another 2 here instead of a 1 from before, so we're going to have 16 over pi sine of pi over 2t. And lo and behold, we can see a pattern emerging here. On the next interval, we're going to have 3 functions on. That's going to give us -12. We're going to have 3 functions on here, so we'll have 3 times all of this. That'll be 24 over pi sine of pi over 2t. And that, as we go down, we can see that the amplitudes of our oscillations are increasing linearly. Every time we go to the next interval, we're getting larger and larger amplitudes. And what that indicates to us is we're still getting resonance in our solution. So even with the Sawtooth function, that jagged drop function for our f external, because the period is 4 and we can get the adding and subtracting, or the pulling and pushing, in sync with the natural oscillations, what we're going to see in the long run is amplitudes that are growing as time goes on, and basically positive feedback in the system. Again, this will be a bit clearer if we see the analysis through a modeling or simulation. It'll help tie this math to what the actual spring mass system is doing.